So what we're really after, though, is not necessarily the strength of the monsoon. Those are nice features. They can tell us something about how we can look at proxy records and see changes in certain features on shorter 10,000 year, 20,000 year time scales. The big thing we're after here are glacial interglacial cycles. Okay, so we'll talk a little bit about glaciers, and then we'll try to wrap this together here. So glaciers, again, for those of us most of us are familiar with glaciers. It's fallen snow that's been compressed, compacted over many, many years, basically ice, gravitational compaction. Okay. The interesting thing about ice is that it's obviously very sensitive to the 0 degrees Celsius line, right? Ice can't form below 0 degrees Celsius. Above 0 degrees Celsius, ice melts. Okay, it has to go through a change phase, which requires a little bit more energy. But we actually know something about sort of the rates of accumulation of ice sheets and the rates of sort of ablation or melt, combined melt of ice sheets. And we know that that's very strongly related to temperature. Okay, such that we have two different curves, one for accumulation of an ice sheet, and realistically this graph is very simple. Precipitation is going to be pretty important. We can have super cold temperatures if we don't have any precipitation, there's no accumulation. So this graph is oversimplified, but what it does show us is that basically if this is mean annual temperature, mean annual surface temperature, and this is accumulation, you can see that we have preferentially more accumulation below at 0 degrees Celsius and lower. Okay. Once we get above a certain temperature here, we're not going to have any accumulation of snow. Over the years, it's not going to snow in areas where the mean annual temperature is 20 degrees Celsius, for example. The red curve here shows ablation. So this is sort of loss of the glacier through sort of sublimation, melt, etc. And that's very much strongly related to temperature, such that as we increase temperature dramatically, we increase the loss rate. Okay, where these things sort of even out, right? Where we see basically ablation being equal to accumulation. This is sort of a transition point for this hypothetical example, right? In this hypothetical example, if you had an equal amount of accumulation versus melt each year, you would have no change per year of this glacier, hypothetical glacier. And so if we looked at this sort of temperature from a temperature perspective, it would be, I don't know, negative 9 degrees Celsius. Warmer than that, melt would exceed accumulation, right? And when melt exceeds accumulation, the ice sheet's going to decrease in size, diminish in size. Whereas on the opposite side, if accumulation exceeds melt, well, the glacier is going to grow over time. Okay. Precipitation is very much neglected here, but we're going to assume that we're actually making some assumption that precipitation does not change with temperature. When trying to understand glaciers, most people just actually think about mass balance, right? Mass balance is basically, was the accumulation less than the melt? If true, if accumulation was less than melt, then you added mass to the glacier, it grew, right? And vice versa, if melt exceeded accumulation, well then the glacier is going to shrink. And by and large, if you think about most of our ice sheets, and especially the sort of the edges of the ice sheets, right? The edges of the ice sheets are areas where it's just on the edge, right? It's kind of in here, right? It's in this area where sort of melt and accumulation are fairly well balanced, and a slight shift in one direction can offset that balance dramatically. Okay? And if you think about the sort of seasonality of when that ice sheet puts on mass versus when it loses weight, it's very much tied to summer versus the cool season. I have winter and summer up here, but realistically there's a melt and there's the accumulation season, and they're very much sort of tied to the warm season and the cool season. Okay? There have been a couple interesting, there's actually an interesting study that came out last week. So most people have heard about sort of retreating glaciers worldwide, and that's true. I think you probably could find 10 retreating glaciers for every one advancing glacier. And so it's sort of like the stock market. When we see the Dow Jones, increase over the last, say, 30 years, not all stocks went up. Some actually went bankrupt, but most went up, right? So it's sort of an index. Is what you usually hear is that glaciers are retreating. There are cases where glaciers actually have been increasing. They have actually been advancing. And here's a couple examples. One is occurring here just north of the Himalayas. And in the IPCC report that came out in 2007, there were a couple flubs in the report that noted that the Himalayan glaciers might be gone by 2035. Which is not true. The Himalayan glaciers are up at super high elevation. They're not even sensitive to temperature. In fact, if you look at the mean annual temperature for some of the glaciers in the Himalayas, we're talking about mean annual temperatures that are out here, right, -20 degrees Celsius. So they're not necessarily affected by temperature. They're more affected by precipitation. Okay. And in fact, what they found in the last 10 years, they've reported that there's been some increase in glacial mass here in a few regions. Okay. And again, that is basically saying something about the rate of accumulation has exceeded melt. Okay. Could be due to temperature. More likely, it's probably due to precipitation. Could be if they had a wet decade, for example, that would increase snowfall and accumulated mass, and that might not have been kept up by the melt factor. I happened to be in Alaska during the summer of 2008, and in the summer of 2008 in Alaska, there was a persistent jet stream overhead. It was cloudy probably about 80% of the time. So to actually get warm temperatures in the summer, usually you need, the sun, okay? And you also do not need to be affected by a persistent jet stream. And what happened that year in Alaska was actually summer temperatures were quite low. In fact, in Anchorage, they were the lowest in 50 years. And voila, this story came out in the Anchorage Daily News saying this was a bad year for Alaska glaciers. Yeah, melt was not very great. Okay, this happens on a year-to-year basis. This battle between adding mass and losing mass happens on a year-to-year basis, and over longer time periods that can be integrated. Okay, so from a large-scale geographic picture of glaciers, we know that typically these form in cold areas, and those cold areas tend to be either at high latitudes on continents, or they tend to occur at very, very high elevations. So there are some really nice tropical glaciers. Okay, you can get some really interesting records from these tropical glaciers. There aren't very many tropical glaciers, but they kind of give you a different signature than the high latitude, Iceland, Greenland type of signatures. But the big thing in terms of understanding this balance between melt versus accumulation is clearly summer temperatures. We can get tons of accumulation during the winter. If we have warm enough temperatures in the summer, we can actually quickly eradicate that mass that was gained over winter. Okay, so summer temperatures are very, very important, and by and large, summer temperatures are driven by insolation. Insolation being the solar radiation at the top of the atmosphere. Okay, for your given point in time. Okay, and specifically here, because 65 degrees latitude north or south is the hinge point at which you see this nice compromise here between ablation and accumulation. It turns out that understanding how summer insolation varies at 65 degrees latitude is pretty important in understanding whether or not you're going to have glacial advance or glacial retreat. Okay. And if you have warm summers, a lot of solar radiation, warm summers, you're going to have melt. Okay, the balance is going to sway towards the melt versus the accumulation. And when that melt occurs, you're going to have a decrease in albedo and more warming and more melt, right? Positive ice albedo feedback. Okay, and there's other sorts of feedbacks that we've talked about that go along with. These are orbits that are really great for advances in glacial coverage. Okay. One has a very exaggerated eccentricity, so that's the one on the left-hand side here, in the eccentric orbit, a very oval orbit, if you will. And in this case, again, northern hemisphere, summer, far away from the sun. Okay, you're gonna dramatically reduce the seasonal cycle and energy when you have this orbit. Okay, so that's a really great configuration to actually have glaciers advance. The other orbit that's really great for having glaciers advance is basically this totally symmetrical system. No tilt, no seasons. It's difficult to get warm temperatures when you have no seasons like this at 65 degrees north latitude. Very, very cold. And once that snow starts forming, it's going to keep going. Okay? So those are great orbits for glacial advance. And realistically, this is a very exaggerated version of where we are today. This is where we are today, right? It's not as exaggerated as it is here, but we're certainly not, we don't have northern hemisphere summer over here. This is what we had 11,000 years ago, right? Northern hemisphere summer, we were closer to the sun. We should have been quite a bit warmer 11,000 years ago than we are today. So we talked about these 3 different cycles, and it turns out that when you have sort of different cycles with different time periods, when you put them together, you get sort of convergence of signals and sort of dilution of signals. And this figure here shows that to some degree. Basically, you can add your 100,000 year cycle to a 23,000 year cycle, and you get something where you see this sort of 100,000 year sort of feature in it, and it's got embedded within it sort of higher frequency period. You can see the other one here with a 41,000 year and 23,000 year. When you put the 3 together, what you see is you still sort of see that 100,000 year cycle. It's not perfect, right? Because there are some time periods where we have sort of confluence of sort of the peaks in the 100,000 year with the 41,000 year, but the 23,000 year one is kind of offset a bit. But by and large, what we see here is the most obvious sort of lower frequency signal here is the 100,000 year signal. But it's not completely exactly 100,000 years. And that's sort of what we see in our glacial, interglacial sort of last million years of climate history. It's very close to 100,000 years. It's 100,000 years plus or minus 20,000 years, which can be very much explained by the sort of convergence here of these different parameters through time. And here's another way of looking at this sort of signature through time, and this figure here shows 2 things. One, it shows you the solar radiation in June at 65 degrees north latitude. Okay, and these can all be estimated through the orbital parameters that we know pretty well. We know these things pretty well. We know where planets are. We know how they rotate through time. We can estimate these things to a pretty high degree, both backwards in time and also for the next 100,000 years if we want to. If we want to play that game, we can do that. So here are the wiggles through time, and again, the axes here's today, here's 600,000 years ago. Okay? And I always look at these graphs and I go, the wiggles do match up, but I see other things. So it takes a little bit of time to look at these and to try to figure out what's going on. But when we see sort of the June 65 degrees north solar radiation, when that's high, right, we can kind of pick out periods when that's been high in the past. So here's sort of, this is our sort of 20,000, 18,000 years ago, 12,000 years ago. This is this period. Okay. And if we look at sort of our ice sheet coverage, this is showing us our last glacial maximum. This is 18,000 years ago. So 18,000 years ago to today, dramatic decrease in global ice coverage. Okay, here's our previous interglacial, right, 120,000 years ago, and other interglacial periods in our past. Okay, and what we can see here is that basically every time that we've actually popped out of a glacial period, it's been provoked by a period where we've actually seen high levels of insolation at 65 degrees north in summer. Okay, so here's coming out of the last glacial maximum, and we get this sort of peak summer radiation. So this is again 11,000 years ago, coming out of the last glacial maximum. That by itself should help to decrease northern hemisphere ice coverage. Increased sort of solar radiation in the northern hemisphere, it's going to help to decrease ice coverage. It's going to help rebound the planet from the glacial period going into an interglacial. Here is the second to last glacial period. It's like 150,000 years ago, and it was, again, there was this period of high summer insolation. Okay, and actually what you see here immediately is that the last sort of peak here in sort of solar or high latitude insolation was quite a bit higher than the one here. That actually got us at the last glacial maximum. Okay, and that we'll return to that idea in a little bit. And for the most part, most of these periods here coming out of the glacial periods, they're all sort of linked to periods where we've seen high levels of solar radiation in the northern hemisphere. These are all things that are going to help with sort of retreating ice sheets. Okay, so that's telling us something about how we actually transition out of a glacial period and into an interglacial period. Okay, a couple more sort of records to do that. Okay, so yes, okay. I'm trying to remember why I have this slide on here. So this slide is just showing again, reminding us of how things have changed. This slow sort of drift towards a cooler climate. Again, this relates back to the last 65 million years, but we have had this slow sort of drift towards a cooler climate, greater ice sheet coverage, and of course, once the climate cools enough, we can actually start to invoke these sort of glacial interglacial feedbacks. Previous to whatever 3 million years ago, we didn't have a cold enough planet to support the sort of formation of large ice sheets on our planet. And if we didn't have that, then we can invoke these sort of orbital parameters in driving the retreat or advance in ice sheets and subsequent changes in global climate. Okay, so this is probably what I just said, but we've had this slow cooling globally, and eventually we get to a point where we have cold enough temperatures to form ice.